In this last module of Chapter 3, Mortality Module 3.7, I described 4 of the 7 mortality metrics covered in the Biodemography book. The first of these is average lifetime mortality, which is the inverse of life expectancy at birth, E0. More generally, the inverse of life expectancy at age X gives the average mortality experienced by a cohort beyond age X. For example, the average yearly mortality probabilities for cohorts with 25, 50, and 75-year life expectancies are 0.04 per year, 0.02 per year, and 0.133 per year, respectively. The next metrics include 3 sets of mortality change indicators. In this case, the subscripts A and B refer to the different parameters at age X, denoting the 2 cohorts A and B. The first set of mortality change indicators include relative increase or decrease, which is the ratio of mortality at age X for cohorts A versus B, and absolute increase or decrease in mortality at age X, which is the difference. The next set are survival change indicators, including relative increase or decrease, which is the ratio of survival or LX schedules at age X for cohorts A versus B, and absolute increase or decrease in survival or LX schedules at age X, which is the difference. The last set of change indicators refer to expectation of life changes at age X, including relative, the ratio of expectation of remaining life at age X, and absolute differences in expectations of life at age X. Threshold mortality is referred to as the left-hand boundary problem, a problem that occurs whenever the actual mortality rate in a group of individuals is less than 1 over n. For example, a mortality rate of mu equals 0.01 cannot be detected with a sample size of 50 individuals. When a single individual dies, the estimate will be at best 1 over 50 or 0.02. as depicted in this graphic, in which mortality is plotted on a natural log scale. In general, it's small sample sizes where there are few individuals at risk. The observed death rates do not provide reliable estimates of the underlying distribution of the probability of death. The last of the 4 mortality concepts or metrics that I will cover in this module involves the general age pattern of mortality in humans. Note the emphasis here is on pattern rather than on scale, as seen in the schematic on mortality in humans, with age on the x-axis and mortality on the y-axis. The primary causes of death are listed at various stages. At the early life stages in humans, newborns experience the highest death rates. Then after the first few months of life, mortality drops quickly and reaches the lowest point of the life course at ages 10 or 11 years. In developed countries, an 11-year-old girl's probability of dying before her 12th birthday is less than 1 out of 8,000. Mortality then increases at a mortality rate through the early to mid-20s, at which point a slight change in trajectory may occur, the details of which depend on gender. Male mortality exceeds female mortality, and the rate of increase is greater for males, resulting in a slight male mortality bump. These differences can be linked to the high-risk behavior more common in males in the late teens and early 20s than in females of the same age. Between ages 50 and 90, the rate of change in mortality with age first accelerates, then decelerates, forming a bell-shaped curve, quite regular for women but not for men. Mortality continues to decelerate from ages 90 to 110, causing a moderate leveling off and slight decrease in mortality at the most advanced ages. The cause of death structure in developed countries progresses from congenital diseases, accidents, and homicides at the younger ages to cancer, heart disease, stroke, and dementia at the older ages. This completes Module 3.7, the last module for this chapter on mortality.